Okay, I'm writing up the key for the Math 43 exam number 1 review, so I thought I would go ahead and film that for you guys. A sports writer wishes to conduct a study on the average pitch count for starting pitchers in Major League Baseball. He wants to estimate the percentage of the time a starting pitcher throws at least 100 pitches in the game. He randomly chooses 500 games and notes the pitch counts for the starting pitchers involved. Identify the population. Well, one good way to help figure out the population is to think about the sample, and he's randomly choosing 500 games. So I would say that since these 500 games are being chosen from the major leagues, which is what he's interested in, I would say that the population of interest is all major league games. So Major League Baseball games, so I'll write all MLB games. So specifically, he's interested in pitchers and pitch counts, but I think that gets more to question B, where they ask what is the variable. I would say that's the pitch count for starting pitchers. And then give an example of a possible data value. So if we went and we selected a game and we watched the game, we might see that one of the pitchers in that game threw 104 pitches. And then classify the variable. So this is where we're trying to get at, is this a categorical variable or a quantitative one? And when you look at your possible data value and see that it's a number, then you know you're dealing with a quantitative variable. And whenever you're dealing with a quantitative variable, you want to think about, is it discrete or continuous? And this can be a little tricky if you read the problem and you see that what he's interested in is the percentage. You might think, oh, a percentage, that's going to be a decimal, all kinds of decimals are possible, so it would be continuous. But the data we're collecting is actually just pitch counts, and pitch counts could be 104 pitches, 103 pitches, 105 pitches, but it couldn't be 104.37 pitches. So I would say the pitch count itself is discrete, because there's gaps between the possibilities. Alright, moving on to problem number 2. According to a January 2012 Yahoo News article, blogging can help calm anxious teens. The study included 161 Israeli high school students who were experiencing some level of social anxiety. The students were randomly divided into 6 groups. 4 of the groups were assigned to blog, 1 group wrote in a private diary, and 1 group did nothing. 2 of the blogging groups focused posts on their social problems, and 2 did not. And one group from each of those 2 options were allowed comments on their posts. So the researchers assessed all of the teens' anxiety levels before and after the 10-week experiment, and the greatest improvements in anxiety levels occurred in the group that blogged about their social problems and were open to comments. So what were the treatments used in the experiment? So it actually appears that there are 6 treatments. And so what are they? Well, 4 of them were blogging. So we have 4 that were groups blogging. You can almost write that, I guess, 4 times. We have blog, 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 blog. And then what were the other groups? 1 group wrote in a diary. And then the other group did nothing. So that one would be one you would consider to be like a control group. And then we don't want to have blog, 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 so what are those 4 groups? So let's see, 2 of the blogging groups focused on their social problems. So we'll say that 2 of these were blogging about social. And so these, does it say what these are? Just that they did not. And then where was the other part? 1 group from each of these allowed comments on their posts. So one of those doing social allowed for comments, and one of those that was not doing social also allowed for comments. So those are our 6 different treatment groups that we have. And did the experiment include randomization? Well, how did it say that we put these students into those groups? It says we randomly divided them. So yes, teens were randomly divided into groups. And did the experiment involve replication? Well, for that you would think about, did they just get 6 students and have one of them do each of these? And no, they had 161 students, and then they randomly split them up. So there's going to be probably several students in each group. So yes, there was 161 subjects in the experiment. There's always the question of, was it enough replication? And that's one we're actually not prepared to answer in this early chapter, but there definitely is replication because they had more than one subject involved in the experiment, and 161, so they actually probably had several in each of the 6 groups. What was the primary response variable of interest? So these are the treatments, but what were they looking to see if it was affected by that? And it said that the researchers assessed all of the teens' social anxiety levels before and after the 10-week experiment. So I think I would say that their social anxiety levels would be the response variable of interest. And then a tricky one, the headline of blogging can help calm anxious teens seems to indicate cause and effect. Do you think this is justified? So it's at least possible to show cause and effect because we did a designed experiment. So I'm going to say yes, because it's a designed experiment. But that's probably just a little bit too quick and generous of a yes. When we say it's a design experiment, that means it's possible that cause and effect is justified. Is it really? We have to kind of look at how well designed the experiment was, and did they have enough replication would be another issue. So one of the things that I would worry about, and so I'll say over here maybe not, one of the things I'd be worried about is they're talking about this could help teens, and they did have teens in their sample, but they were all Israeli teens, so it's not really representative of all teens. It's certainly possible that what is working for the Israeli teens would generalize to all teens, but it would be better if we had an experiment that involved teens from all over the world, if we're going to talk about teens from all over the world. And then, was there enough replication would be the other issue. And so it says the greatest improvements in anxiety levels occurred in the group that blogged about their social problems and were open to comments, but it doesn't actually say that was a significant improvement compared to the other groups. It just says it was the greatest. And typically the way we get our feel for was this enough replication or not is if they state somewhere in there it was a significant difference, then even though we don't know the math yet, that indicates that the people who do know the math have decided that was a big enough difference that for that replication amount it mattered. So I'm just going to put a question there. Do we have enough replication? Because if you have 161 and you divide that by 6, what would that be? I'll just do some calculations over here on the side. 161 divided by 6 is about 26.8. So there's around 25 to 30 students probably in each group, and that's not considered a real large sample size. So without knowing how big of an improvement difference there was in that group compared to the others, it's hard to say whether that was significant or not. And then finally, discuss how data ethics should have been addressed in this study. Whenever you're doing a design experiment and people are volunteering, you want to get informed written consent. And probably that should be including the parents, right? Not just going and having high school students participate and their parents didn't even know. And then the other thing is to maintain confidentiality. We have these teens that are expressing their social concerns, and they might be putting some very personal stuff there, and when we write up the report we wouldn't want to name them specifically along with their social problems. Okay, continuing on to page 3. In 2006, the Pew Research Center asked a random sample of 3,014 American adults how happy they were, and the results are summarized in the chart below. Use the graph to estimate the percentage of those sampled that were at least pretty happy at that time. So at least pretty happy, I would say, includes the group pretty happy and then very happy, which would be more than that, so at least. And so I want to add the folks in those two categories together. And they want to know the percentage, which would be the relative frequency converted over to a decimal. So I'm just trying to gauge as best I can on this graph how tall each of those bars are. It looks like for pretty happy it's about 50%, and for very happy that's maybe 32, 33%. It's just somewhat of a guess based on the 30 and the 40 there. I'll go ahead and go with 33. So if I added those together, I'd have 0.50 for the pretty happy and 0.33 for the very happy, and that would be 0.83 altogether, and then moving the decimal over, that would be 83%. Again, that's just an estimate based on my best read of how tall those bars are and using the scale. And then use your answer to part A to estimate the number of those sampled that were at least pretty happy at that time. When you first read that, you might think it was the exact same question, but on the last one, they asked us to estimate the percentage, and now this time they're asking us to estimate the number. So we thought that the percentage was 83%, and then from those sampled there was 3,014 people. So I would say of those 3,014, we're estimating that 83% or 0.83 of them were at least pretty happy. And then we want to just bring in the calculator there to do that calculation. And that comes out 2501.62. So I'd probably round that to the nearest whole number and say approximately 2502. So I would say about 2,502 of those sampled were at least pretty happy. So one was the percentage straight off the graph, and then using that percentage times the number that were sampled, we can convert that over to a number that were at least pretty happy. Alright, moving on to number 4. In January 2012, the author of this book, that'd be me, collected data on all 109 of his Facebook friends. I have a few more now. And the number of wall posts for each of his friends is displayed in the stem and leaf diagram below. So this is actually part of StatCrunch, or at least it used to be. I think it's still there. There's a like Facebook button you can click, and if you sign into your Facebook account, it'll give you all kinds of different stats on your friends and their posts and stuff like that. So it might be something you wanted to play around with on your own, perhaps. So we have the stem and leaf diagram here. One of the most important things to note about this is it says the leaf unit is the tens place. If I didn't read that note, I would probably read these numbers down here 62, 68, 69. But if the unit is the tens place, then that doesn't represent 8, it represents 80. That doesn't represent 2, it represents 20. And that would mean this has to be the hundreds place. So this isn't 62, it's 620, and this isn't 68, it's 680. Now it's actually probably 680 something. It could be 680, 688, 687, we don't know, but 680 something. And so this one down here wouldn't be 100, it would be 1,000. 10 hundreds plus the 0 would be 1,000. And then let's go ahead and emphasize that by just taking what we were just saying and writing that down. So write out the approximate values for the second use of the 3 stems. So these are our stems on the left. That would be the second time the 3 stem was used. So it says the approximate data values because I don't know what they are for sure. It's 300 plus 50. So I'm going to say 350. But again, it might actually be 359, 358, 350, 353, who knows. And then the next one is another 350. And then we have the 8, which represents 80, so 380. And another one of those. And then the 9, which represents 90, so 390. And then if you considered each row of this graph to represent a class from a group data table, then what are the class descriptions for the last 2 classes? So here's our last 2 classes right here. And this would be the 900s, but it's split into 2. So the lower class would be the lower 900s, this would be the upper 900s. So the upper 900s would go from 950 through less than 1,000 or through 999. It would really depend on whether this was a discrete or a continuous data set. So I'm going to go up there and have a look at that. It says that what we're looking at is the number of wall posts, and the number of wall posts you have can't be a fraction or a decimal, it has to be a whole number. So I would say this is a discrete data set, and so the through symbol is appropriate, and I would say 950 through 999 would be that second to last class, and then the next one would be starting at 1,000, and you might be tempted to go to 1,099, but remember it's 2 lines per stem, so that would just be like the lower half of the thousands, and that would only go through 1,049, and then 1,050 through 1,099 would be the second use of the 10, which didn't show up, so these are our last two. And then what percentage of the friends have at least 500 wall posts? So 500 would be on this first 5 lines, so go ahead and draw a separator right there. Anyone that's below that mark had 500 or more wall posts, so at least 500. And so how many people was that? 1, 2, 3, 4, 5, 6. Let me just double check that. 4, 5, 6. Yeah, so there were 6 of them. So 6 out of how many? Well, at the time of this, there was 109 friends, it says. So that would be 6 out of 109. And if I do that on the calculator, 6 over 109 is approximately 0.0550. And then they want to know what percentage of the friends that would be. So I'm just going to move the decimal over and put the percentage symbol. So 5.50%. So not too many of my friends had over 500 posts. It was a small percentage, just over 5%. And then, based on this sample, what is the best choice for the likely distribution of the population from which this sample was taken? So that's a little bit of a tricky question because this is all 109 of my Facebook friends, but I guess we could imagine this to be if I started adding more and more friends and I got all of the friends that I could possibly have, what would the shape be? And if I look at this sample, I'm going to go ahead and turn this sideways so I can think left or right. The peak is over here at the first bar, and then it seems to drop somewhat steadily down. There's a little bit of bumpiness, which I would attribute to random variation, and then settle down over here to the right. And so it seems like we just have this tallest bar and then tailing off to the right. I would say that looks most like right exponential to me. So if I had to guess, I would say that right exponential is the best choice. And just a reminder, if you were thinking severely right skewed, right exponential is the most severely right skewed distribution, so you would be in the right category. I just think it's more appropriate to call it right exponential because the tallest bar is at the very left edge. Hey, moving on to number 5. For 15 randomly selected days, I kept track of the number of diapers used per day for my 7-month-old niece Sophia. The data is shown below. We wish to get a sense of her overall diaper usage, and they give us the sum of the x squareds for this data set. Just a quick comment, whenever you see that given, you should expect that you're going to go ahead and use your calculator to do a lot of the work here because that number is only given to verify data entry on the calculator. So calculate the mean of the data set. Notice down here, calculate the standard deviation of the data set. So I'm going to go ahead and do that using the calculator. So that means step 1 is to get all the data entered in. So I'm going to press the stat key and choose edit and enter all of that data into L1. So 787, 797, 8, 13, 5, 5, 9, 10, and 8, 8, 10. And then I want to go ahead and have the calculator do the mean and standard deviation calculations for me. So I'm going to press the stat key, go over to calc, choose one variable statistics, and then tell it where my data is, which is in list 1. And so when I do that, it's going to give me a mean and standard deviation, but first I want to check that the sum of the x squareds matches up. So they gave me 1,033 over here, and the screen here says 1,033. I'm not using that number to calculate the mean or the standard deviation. I'm just using it to verify that I've entered my data correctly. So let me go ahead and set this aside for a second. When we do our mean and standard deviation, even though they say the mean and the standard deviation, there's really no such thing. There's sample means and there's population means. There's sample standard deviations and there's population standard deviations. And the mean and the standard deviation doesn't specify which kind it is. It says here that we wish to get a sense of her overall diaper usage. Well, unfortunately for her parents, she's going to be in diapers for more than just 15 days. So I would say that this is just going to be a sample, and it says it was for 15 randomly selected days, which also indicates that it's a sample. So those two things together indicate to me that we're looking at sample data. And if this is sample data, then when we refer to the mean, we would call it X bar. And when we refer to the standard deviation, we would use an S for that. So now if I bring the calculator back in, it did give me X bar, and I need to put at least one decimal place more than the original data. So at least one decimal place. I could put just 8.1. I'll go ahead and go a little bit further and just put 8.067. But again, 8.1 would be okay. The rounding rule says just go at least one decimal place beyond what we have here. And remember, those rounding rules are on your formula sheet, so have that with you as you're doing your review. And whenever you're not sure about a rounding rule, look that up on the back side so that you're used to doing that when the test rolls around. And then for the sample standard deviation, the calculator gives both S and sigma. We'd use the sigma if it was a population, but this one is a sample, so we'll use the value of S, which is 2.0166. It's a 5, but followed by a 9, and the rule there is 1, 2, 3, 4, 5 digits as a minimum. You could put more if you want. That's the minimum that you could put. And then just one last note on the calculator. If this had been population data, then we would have used sigma, and we still would have used the 8.067, but we wouldn't have called it X bar. We would have called it mu. And then for the median, I'm going to go ahead and start out by calculating the location. I'm going to add some words here, and maybe this will be on yours by the time I print it, but when I put this on the test, I always ask people to show their work for the median, so I'm going to add that. And that means do a calculation of the location. That would be 1/2 times the number of data values plus 1, which would be half of 16, or 8. That does not mean that the median is 8. It means that the location of the median is 8. So let's go see what the actual number is. And remember that when we talk about the 8th value, that's the 8th value in the sorted list. So I'm going to hit Stat, and in the Edit menu, the second option is Sort A, and I'm going to do a Sort A of List 1, so sort ascending from small to large, List 1. It says Done, and now I'm going to hit Stat and Edit again, and I'm going to go in there and see what the 8th value is, and this time it turns out to be 8. So that's a little confusing, actually, that the location of the median turned out to be the same as the median. That is, in fact, very rare. So make sure that you're always doing both steps. Calculate the location and then go look at the list, and whatever the 8th number is, that's your median. In this case, kind of a little bit of a surprise, it turns out to be the same value for the 8th number as the location. And then, would you describe this data set as left skewed, right skewed, or neither? Well, the way we do that is to look to see which way the mean has been pulled, and the mean seems to have been pulled to the right of the median, but also I would say not very far, because it's almost the same for these two values. So I would either say neither or very slightly right skewed. And again, the way we look at that question is which side of the median did the mean land on? And here it landed on the right, so that's why I'm saying right skewed, but it's so close to being the same that I feel like neither is almost appropriate, or if you're going to say it was right skewed, it would be very slight. And then which of these measures of center would be best for planning how many diapers to buy for the next 15 days, and explain? Well, one of the things that we said in the notes when we were trying to choose which measure of center to use, we said that if the total was important, then you'd want to go with the mean. And here, when we're thinking about how many diapers to buy, it's the total number that she's going to use up that would matter, not what was typical per day, though it kind of in a way doesn't matter too much because those are about the same. So I would say to use the mean, and for my reason I would say because the total number of diapers matters. And we also say that it's good to use the mean when your data is not skewed, and our data is either not left or right skewed or maybe very slightly skewed, so the mean's good in that sense too. But I think the more important factor here is that the total matters. Alright, moving on to the last problem, number 6. We have a random sample of 115 college students were asked how much they paid before tax for their current cell phone, and the sample produced a mean of 107.79 and a standard deviation of 83.12. And just a quick comment, since it was a sample, the mean they're talking about would be an X bar, and the standard deviation they're talking about would be an S. And then they want us to know, would it be unusual for a student to have gotten their phone for free? And so let's see how the calculation comes out on that. When somebody asks me, would it be unusual, I always want to do a z-score. And in this case, I would do x minus x bar over s. And I have to think about what is the x if the phone was free. And we're talking about the cost that they paid. So if they didn't pay anything for their phone, if it was free, that would be a 0. And then I would subtract the mean, which is 107.79. And I would divide by the standard deviation, which is 83.12, and I would want to see how big that is. So let's see, let's exit out of here, clear that. So 0 minus 107.79 divided by 83.12 gives a z-score of negative 1.2, and then it's 9.6, but that's followed by 7, so I'd write 9.7 there. So there's my work, and then would it be unusual? Well, things are considered to be unusual when they're more than 2 standard deviations away from the mean. This is about 1.3 standard deviations away, so I would say no, it's not unusual. No, because free, which is a 0, is less than 2 standard deviations below the mean. Just got to remember there that 2 is our cutoff between what's expected and what's unusual, and the z-score is telling us how many standard deviations free was away from the mean, and it was about 1.3, so that's less than 2. And just another reminder, if you look at your formula sheet for the rounding rule on z-scores, it says exactly 3 decimal places. So on this I would want to see a 1.297 or negative 1.297, but not a 1.30 and not a 1.2968. Exactly 3 when we do our z-scores. And then would it be unusual for the student to have paid $300 for their phone? So we just do the same idea there. We do the 300 in place of the x minus the x bar of 107.79. We would divide by the standard deviation of 83.12, and then we'd see how that comes out in terms of the z-score. So I'd go to the calculator on that one just like the last one. The parentheses are important on your numerator. If you forget that part, you will get a wrong answer. And I get 2.312, again going to exactly 3 decimal places on that. And this time it's going to be a yes because 300 is a little over 2 standard deviations away from the mean, and we just said anything more than 2 would be unusual. So this time it's a yes, because $300 is more than 2 standard deviations above the mean. And so the main thing you want to remember there is that kind of word trigger. If you hear them ask would it be unusual, then you want to do a z-score, and then their cutoff for that is 2. less than 2 standard deviations away from the mean, not unusual, more than 2 is unusual. And then finally on that, what amounts would make up the expected range for the phone prices? That is, what prices could a student have paid and it would not be considered unusual. So it would not be considered unusual if it was less than 2 standard deviations away from the mean. That's what we consider to be our expected range. So I would take x bar and I would subtract 2 times the standard deviation, and I would take x bar and I would add 2 times the standard deviation to create cutoffs. And just plugging the numbers in there, that's going to be 107.79 minus 2 times the standard deviation, which is 83.12. And then here we would do the exact same thing, but we would use a plus sign. And then I'm going to go to the calculator for both of those. So 107.79 minus 2 times 83.12. And then I'm going to do second enter and change that to a plus. And I get negative 58.45 and positive 274.03. And this is not the answer, but these are the boundaries on that answer. And when I give the answer, I want to think about the actual variable, which is the cost of the phone before taxes. It can't be negative. The cheapest it could be would be free, and then anything below this 274.03 would also be in that expected range. So I guess if this was a continuous variable that could be negative, I would say the expected range is anything between negative 58.45 and 274.03. We usually would just leave the numbers alone and use the word between. But because negatives don't make sense for this example, I'm going to say it's anything from free, or $0, up to, but not including, $274.03. And I say not including because if the phone did cost exactly $274.03, that would be 2 standard deviations away, and we would consider that unusual. So here's my answer. I expect the phones of students to cost anywhere from $0 or free to less than $274.03. So that's our expected range. Again, it could be anything in this range, but I don't expect that you're going to get paid to take a phone. It may be free, but I wouldn't expect the negative to make sense. So I would cut off the lower end at 0 and then say anything up to less than 274.03. All right.